Finally, we have a talk by Ionatan Kuperwajs.
All right, so hi everyone. I'm Ionatan. I'm a PhD student with Wei Ma at NYU. And today I'm going to tell you about some of the work we've been doing at the intersection of cognitive modeling and deep neural networks, and specifically how we can use neural networks to inform cognitive models. So in the lab, we've been mainly guided by the following question, which is how do people think ahead? And a little bit more formally, that's known as planning, which is defined as the mental simulation of possible futures. Now, planning is a hallmark of human intelligence. Here are just 3 examples of real-world behavior in which agents, humans or animals, in which it is beneficial for them to think multiple steps into the future, evaluate their actions and the consequences of those actions, in order to arrive at a decision that is best in the present. Now, if we want to study planning, of course, we need a task to do so. And we like to think of the space of planning tasks across 2 dimensions. The first is the complexity of the task, which you can just think of as the number of states in the task, so it's state space. And the second is that task's tractability for constructing process-level models of human behavior. Now, your first thought when brainstorming planning task might be, why don't you just use something like chess or Go? And that's exactly what the field of AI has done. These are really complex tasks in which we can build really cool algorithms that outperform human abilities, but they're not yet tractable for building cognitive models. The safe space is just too large to really do so. On the other hand, cognitive science has taken a more reductionist approach, using simpler tasks, but gaining a lot of insight into how humans think and behave in these kinds of tasks via computational modeling. And in the lab, we've been thinking a lot about how we can sit sort of in this middle space, using tasks where we can push the complexity in terms of the state space, but preserve computational tractability. So 4 in a row is the task that we've mainly been developing in the lab, and one that I've been working with for the majority of my PhD. And it's a 2-player combinatorial game where 2 players alternate placing pieces on a 4x9 board, trying to connect 4 in any orientation. So here is a game between 2 humans that I'm going to show in black and white. And I hope that you can appreciate just by sort of watching this video that while the rules of the game are pretty simple and intuitive, it's easy to explain, there's still quite a bit of nuance and complexity in the task. So here, for example, you'll see in a second that black only wins because they create this double threat with this 3 in a row that white can't defend against, and then they win by completing the 4 in a row. So I'm going to be talking a bit more about our modeling efforts with this task, and specifically the neural network aspect of them. But if you want to check out more details on what I'm going to give about the cognitive modeling or all of our in-lab experiments, you can check out this preprint. Okay, so about that cognitive modeling, so now that we have a task, we'd like to build a model to explain what humans are doing. And the standard approach to this would be as follows. So we'd use our intuition about the task to handcraft a model and specify free parameters, thinking about what goals and sub-goals maybe humans like to engage in and think about. And eventually, we're going to want to evaluate how good that model is, maybe by comparing it to data. We're going to do so via model fitting. So let me quickly go through what we've come up with so far. So the main sort of takeaway is this is a state-of-the-art planning model inspired by classical AI that has 2 main components, a value function and tree search. So the value function computes how good board positions are by doing a weighted sum over players' features and subtracting off a weighted sum over their opponents' features. These features are all intermediate steps to winning the game. A bunch of examples are highlighted on the board. So you see like a connected 3 in a row with a space to complete the 4. You see a bunch of different 2s, 2 in a rows with spaces to complete the 4. Of course, the 4 in a row feature also is important and tells a player if they won the game. And we additionally add a centrality feature that captures how close pieces that are played are to the center of the board, since generally it's better to play closer to the middle. The tree search component then is a version of best first search, where the model evaluates the most promising moves using the value function that I just outlined, assigns them some quantity. and then considers future actions that the player might make and that their opponent might make in response to those, evaluates those, and continues on until sort of the top valued move has stabilized for a number of iterations. There are a lot of model details that I'm skipping over here, such as pruning in the tree search, a bunch of sources of noise. Those are all in the preprint. I'm happy to also take questions about them later or talk offline if people are interested. So now that we have a model, we can fit it to human choices and evaluate it in a variety of ways. In the preprint, we do a lot of model comparison in different experimental variations. Let's say that we've done that, and now we want to go and actually make our model better. And we do that via a process called model improvement. Now, a sensible approach to model improvement might be to change the model iteratively by looking at the largest errors that the model makes in comparison with the data. So if we actually do that, here's an example board where the error is quite large. Here you see the user is playing black. White is an AI agent that's just a version of the planning model with tuned parameters. And the move that the human actually chose is in a solid circle compared to the planning model's prediction in this dashed circle. The planning model's move that you see is predicted makes a lot of sense. It creates a feature for the current player. It's pretty close to the center of the board. But the one that the human actually made is near the opponent's piece, so that makes a little bit of sense, but it's definitely far from optimal in this top right corner. Similarly, here's another position in which the human has the opportunity to create, to actually just win the game and complete this 4 in a row, but they overlook this immediate win. And here is just a third example where the user makes sort of a seemingly random move towards the top left here, when in fact they could have created a threat by connecting 3 pieces in a row. Now the point here is really that this is a complex task, and when you're comparing the largest residuals between a cognitive model, the planning model that we have, and the data, these are often noisy and really impossible to capture with any data, with any model, sorry. And so this might not be a good approach for improving our model. So the alternative that we're proposing is to use neural networks trained on human behavior, importantly not on the task itself, like AlphaZero or other neural network models that you might be familiar with. And the purpose is to establish an absolute goodness of fit for any model on the data set, and then compare that neural network or that powerful model against the planning model or the cognitive model that we already have, rather than comparing that planning model to the data. And we can do this because deep neural networks make minimal assumptions and have the capacity to represent almost any computational process. The network can detect patterns in the data without human understanding of those patterns ahead of time, so they can help with this discovery process. Once we've trained the network to predict human behavior, the model can be compared to the network to judge whether there's still room for any kind of model improvement and in which situations to actually make this improvement. The reason that this works is because you can think of the network as pooling information across trials and being sort of a smoothed out, less noisy representation of the data to compare against. Now there's some past work using neural networks to improve modeling in this way, used with simpler tasks and data set that often require these complicated recurrent architectures or outside of the planning domain. So I'm going to focus on this complex task and specifically on planning for this talk. Now, one obvious caveat here is that neural networks require large amounts of data in order to train. And so to address this, we scaled up 4 in a row by partnering with Peak, which is a mobile app company that put our game on their platform, and then they sent us back anonymized data. So here's how the gamified version of 4 in a row looks on their platform compared to our in-lab version. Now, some features of the data set. So these are human versus AI games where the user always plays first. Like I mentioned earlier, the AI is a version of the planning model, and we can tune different parameters of the model to make the agents stronger or weaker. The data set currently consists of 10.8 million games from 1.2 million unique users. So it's really large, and we're actually collecting still more data, so it's going to get even larger. And to sort of just drive home that point, here's a histogram of the number of games played by all users. And you see there are many users here that just play a few games. But if we blow up the scale, we see that there are thousands of users who have played even up to 100 or more than 100 games. We really have a wide variety of users. Okay, so now we actually want to build the networks and predict human play. And our philosophy in terms of architecture was to use the simplest architecture that would perform well on this prediction task. So let me walk through that. So we start with two 4x9 boards as input, one for the user's pieces and one for the opponent's pieces. This input gets flattened into a one-dimensional vector. And then that gets passed into a hidden layer, which I'm outlining here in red. And that contains a fully connected layer, a nonlinearity, another fully connected layer, and then some input that it gets from these skip connections from the input of the hidden layer. That's just to avoid the vanishing gradient problem. Now, we want to get an upper bound on predictability in terms of human behavior. So we need to scale up the networks so that we actually achieve some kind of upper bound. And to do this, we increase the size of the network in two ways. One is by chaining together these hidden layers, the thing outlined in red here, and another is by increasing the number of units in each of these fully connected layers. And now finally, we have a fully connected output and a softmax that gives a probability that the human played on each square of the board. So that's why I have this 36-dimensional vector, since there are 36 squares on the board. Okay, so here are the details for training these networks, and I want to emphasize that because we're using such a large data set, we don't have to worry too much about overfitting, so no regularization or anything like that. Here, just to validate, that's the learning curve for the best network that we had. And then in terms of scaling up the network, here's the test likelihood as a function of the number of hidden layers and the number of units per layer. And this shows that we reach a reasonable upper bound on the data set where we can further increase the size of the network, of course, and maybe get a little bit better in terms of the log likelihood, but it is plateauing, and we're pretty happy that increasing the size further is not going to give us any significant gains in terms of predictability. Okay, so now we have a network, we have it trained, and we want to validate that it actually provides a good fit to human behavior. And so we did that via three methods, which I'm going to show for the largest and best network that we had. So the first method is accuracy, which is sort of the first thing that you might think of, and we're plotting this as a function of the number of guesses we give the network to guess the human move. At one guess, this is already above 40%, which is much higher than chance, and spoiler, much higher than what the planning model achieves. And this quickly increases the more guesses you give the network. The second is the entropy of the network's output distribution, which we break down in terms of move number across gameplay. So this shows that the network is less confident in its predictions early in gameplay, and that makes a lot of sense. There are less pieces on the board, less features on the board. Human behavior is naturally more variable. And the network becomes more confident in its predictions as the game unfolds, and where humans play becomes a little bit more consistent. And finally, we wanted to look at if the network captures general trends in human gameplay. And we did that with a set of summary statistics. So here's an example of one where we're looking at the distance to the center of the board of each piece played, again broken down across gameplay. The data here is in black circles, so that's actual human moves. We provide a random model for comparison in green. And the network is in this blue line, which you can see is matching the data pretty much almost exactly. And we did this for a whole set of summary statistics, such as distance from certain pieces on the board, threats made and threats defended. And the network pretty consistently matches human behavior, which is a good indication that the network is a good summary of the data, which is what we set out to do. Okay, so now to compare the network with the planning model and get to some of the model improvements, the first thing we did was check that the network outperforms the planning model. So this is indeed the case. Here it's broken down by individual move predictions in terms of the difference in log likelihood per move. And here it is also by average accuracy as a function of move number. And we're comparing here with a planning model that we have developed quite a bit in the lab and has gone through a lot of the standard iterations in terms of improvement, and yet there's still sort of a space for additional improvement even beyond that. Okay, so this gives us a subset of board positions that we can systematically explore, where we're going to look for patterns in behavior that the network correctly predicted and was able to predict that the model doesn't yet capture. So here are the same uninformative boards that I showed earlier that show the differences between the model and the data, the largest ones. Now I'm overlaying the output for the neural network in red on top of everything that was there before. And I just want to point out here that the network's output matches the model, which validates that these are truly noise, and even that a very well-fitting neural network can't really capture what humans are doing here. And now if we do the same exercise but compare between the model and the network, we get much more interesting board positions. So here's one where the network correctly predicts that humans defend against a loss in this bottom right corner. The model overlooks this because it plays more centrally in a very offensive position when there are a lot of good features for the current player, compared to this corner position where it's obviously important because you're defending against a loss, but there are no features for you, so the model prunes it away in its first step of search. Here's another where the network correctly understands biases that humans have to play away from the center in some positions and closer to pieces. And a third where two moves are pretty much equally good, but the network knows that humans will want to defend against the opponent's pieces even if they're not posing an actual threat. There's no way to connect 4 in a row here for white. And similarly, humans have a tendency to play a little bit closer to their own pieces. Okay, so we looked at a lot of these different board positions and categorized them into 5 patterns that are going to guide our model improvement process. This is ongoing work, so stuff that we're still working on now, incorporating into the cognitive model and seeing if it actually improves the fit and teaches us something about planning. I'd like to focus on this top opening bias, just as a sort of first step proof of concept about how this might play out. So this opening bias category, we basically noticed that early in gameplay, people prefer to play towards the top left corner of the board. And this is especially evident in people's opening moves. So if we wanted to actually try to fix this for the opening move, one preliminary first pass idea might be to use the histogram of the opening moves, actually taken from data, and add a parameter to the model that weights this histogram rather than using a centrality feature in the opening move. When we actually do this and implement it into the model, the fit does improve, and we can predict a larger number of moves correctly, which are mainly the moves in which the user plays first. And in future work, we're going to implement model changes for sort of all of these categories, and I'd be happy to take questions about that or discuss that further with other people if you have ideas. Okay, so the conclusion from this talk is hopefully that there is a little bit more of a guided approach to model improvement in which we can use neural networks when it's possible to do so. So just to wrap up and summarize, we provided a framework for model improvement using deep neural networks. We trained these networks to predict human moves in a planning task, ensured that the best network represents an upper bound on how well any model can fit the data, and then looked at positions in which the network is more accurate than a model of human planning, which led to these candidate mechanisms for model improvement. So thanks to Weiji and the entire lab, and especially to Heiko, who's sitting over there, who's a postdoc that's been advising me a lot on this project. And I don't know if we have time for questions, but I'll take any if there is.
Yeah, we have 1 or 2 minutes for questions.
If not, I'll just wrap up. That's fine too.
Anything on Zoom? Can't quite hear you.
Okay, so if you don't have any questions, close this session. Thanks for joining.
Yeah, I'm not sure if someone's asking a question or just their mic is off right now.
Okay.
Okay, I guess we'll wrap it up then.
All right, I'm just going to assume that's noise. But yeah, I guess that's it. Thanks for coming.
Thanks, everyone.